Okay,ครับ. You remember when I said the first class we met, the first time we met, I mentioned to you that I'm not really a big fan of using PowerPoint to teach. Okay, it's a very easy thing to do. You know, I just write like a whole set of slides and I just use it everywhere I go. It's very lazy way of teaching. And I guess I've done that professionally because sometimes I just don't want to spend too much time preparing new slide every time I have to give a talk. But for a real, interactive class, hopefully, which is what Basai curriculum is going to be, I try to discourage, even amongst faculty. Okay, the junior faculty, sometimes they fall back on using PowerPoint because it's easy to fall back on, but it's not a good idea. Anyway, opposite of PowerPoint is something else that I want to tell you that I use, which is called a mind map. Now, mind map really is with PowerPoint, right? It's pretty much Microsoft. With PowerPoint, you're pretty much stuck, I think, to Microsoft. But mind map, you can use anybody. Okay, I happen to use Xmind. I never pay for that. I just use the free version, so that should be suffice for everybody. So this is my Xmind, right? I use my Xmind for a variety of things. If you notice, right, this is in the form of a notebook, okay, of a text. So it's going to be interactive text. I'm actually, writing a book, but interactive, okay? But you notice when I try to plan the topic, right, I want to see if I cover everything and how they relate, right? So the way to keep track of that, you notice, okay, I have all this thing like, 2.2, 0.3, 0.4 and whatnot. I actually keep track of it here in mind map. Okay, mind map has many topography, so it can have sort of like going back and forth or down and up. But in this case, for example, I'm just using using it as a representation of an outline. So I keep track of my, which chapter I have written. So I've written maybe this chapter, this a different section. And if I've written it, maybe I'll make some note. If I haven't, okay, so I make a note that I wrote this section already, but this is just topic that I have to come back to write later and so forth. So it's quite a visual way of organizing yourself. So I really encourage you to take mind map as a tool. I happen to once again use Xmind. See, 782 days evaluated. So I've never really used I just use a free version. Okay. So I use this to actually keep track of my own writing project. Okay. So one writing project. Now, okay. So today I want to give you a little bit of an overview map of the mathematics you need. Okay. And this is a particular kind of mind map. It's called like a fishbone or something because it looks like a spine and then have a thing sticking out. It's called fishbone. I use it to plan the curricula for Basai, the 4-year journey from left to right. But anyway, so, okay, let me share. I forgot to share the screen. Thank you, Ka. Okay, Kap. So if you look at this, at the top level, okay, there are only 4 things. Okay, there are only 4 things that you absolutely need as a mathematical background to get you through Basai. Okay, so one is the very basic elements of numbers. Again, numbers is not something difficult, but like I mentioned to you last time, a lot of time if you don't understand or appreciate the number scale, you can be a very proficient programmer and make some silly data science conclusion. Okay. So number counting, this is all something that we were being a little bit philosophical last time, to be honest with you, right? I was saying you know how to add 2 numbers together, but I want you to stop thinking of adding 2 numbers. I want you to think of an operation that requires 2 things to complete, and then you supply A and B. So A plus B becomes defining a function that does something with 2 ingredients. One ingredient is A, the other ingredient is B, and the operation you do happen to be very symmetric. A plus B is equal to B plus A. But in the future, it may not be symmetric, right? It may be internally created from different function. Okay, you can have function that calls other function, right? Okay. So that was the I guess deeper understanding of meaning and function and mathematics that I want you to have. So it's a kind of abstract thought, right? But toward the second half, I guess, I start to talk about relation, operation, function, equality, and so forth. So these are the nitty-gritty, again, something you did in grade school, right? A plus B equal to a C, okay? And I say, well, equality has two meaning, right? It's an equality. What is it? It's an assignment. This is equal to hand. Okay, that's my assignment of this object to a word in English. Okay, I say this is equal to this, meaning the number of fingers I raise is equal. So that's checking. Is it equal? So it's a true and false, right? And I can also define function. So equality has it's the main syntax of mathematics and programming. Okay, it's like the verb. It does everything. You can't just learn the language knowing the vocabulary without the grammars and the verb, right? Same thing with mathematics. You have the objects, the numbers, but you have the operations. And to make the sentence, like you do the operation on the left and set it equal to the right, or keep it temporarily to the right. That's equality. Okay, that's assignment. Okay, so these two are basically the nitty-gritty. Okay, it's not something that you haven't learned. It's something that you've done automatically. But I want you to take a step back and be more conscious about the abstract meaning of it, because you are going to complicate things when you start programming, start talking about machine learning and so forth. Okay, so that was the I think last week, not last week, 2 days ago, I did give you the saying, right? The Thai saying that you ride an elephant to catch a little bug, right? Well, the idea is that you ride an elephant to catch a bug because you want to be proficient at riding an elephant. Then you catch something else, a lot more bigger, a lot bigger than a bug, obviously. Right. Now move to the right-hand side here. Basically, I will expand this later, maybe some for I'll give this to Chris or something who's going to keep you maths. Basically, linear and algebra. Okay, linear algebra is what's going to get you throughout life, I guess. Now, what's linear algebra? There are two things in linear algebra. Okay, you don't have to look at the note. It's not here. I'll show you in the Mathematica. Algebra. Okay, again, I'm going to spend 1 minute being very abstract here. Okay, algebra. By the way, algebra is an Arabic name. Came from a in the during the time when the Western civilization was in the Middle Age, the Arabs community was very enlightened in science. So I can't pronounce this guy's name, Al-Khwarizmi or something, but eventually that becomes the word algorithm. Same thing with algebra. Some a lot of these words are from Arabic name. Anyway, algebra in Thai, I think P-chakanit, you know it as something like x plus 2 is equal to 5, so x is equal to 3 or something like that, right? Okay, that's not the essence of algebra. The essence of algebra is what's called a closure. Okay, it keeps things within bound. What do I mean by that? Okay, if I add two numbers together, I get something else, and that something else is also a number. That's the sense of closure we're talking about. That's what I mean by algebra. You have two things, you operate on them, and the result is still in the same population. Okay, it's a little bit like biological reproduction, right? A human species, right? Homo sapien is an algebra because you can take a dad sample and a mom sample, then you get married, then you have babies, but the baby is always the same species, right? Right? And so forth. Now, algebra, a sense of algebra when you study mathematics in college is a bit like that. So there are other algebra. There are really fancy computational model and so all sort of stuff. But the essence is you take something else, you do some kind of operation, and the result is still belong to the same population. Okay. So that's abstract meaning of algebra. Okay. But you learn just the simplest kind of algebra is called linear algebra. It's saying that you work on things. Now, I haven't said a number yet. I haven't said it's a number. It will be some kind of a number, but you have something, you have some operation, you do something to maybe this pair of operation, a pair of things, and you still get something, and you can do more operation because, you know, it's still human. Let's put it that way, right? So dad and mom gets married, have kids, kids grow up, becomes adult, gets married and have kids, right? So you never have like a two, say, elephants get married and they have a baby giraffe or something. Okay, that's not an algebra. Okay, so what makes algebra important is you have the operation that maintain the consistency between the input and the output. Okay, and this will come, subtle form of this will become relevant when you go to machine learning, because you want to extend the notion of what you're working with. If you're working with number, yeah, that's obvious, right? Okay, I'll tell you an example, a very quick example. What's not an algebra, right? Numbers, positive numbers, and plus and minus. Because you can take two positive number, 5 and 7, and you say plus 5 minus 7, you get -2. That's no longer part of positive number. Okay, so you see what I mean? So that's silly. Nobody would ever define algebra consisting of this positive number, but that's what I mean. Okay, right. So come the term linear. Okay, linear, by the way, is a misnomer, but roughly speaking, okay, I just throw the word out just for fun, for trivial. Okay, a lot of things you'll be doing is called affine, not linear, but we'll use the word linear because it's the easiest thing to your ears. Linear just means a sense of proportionality. Okay, sense of proportionality. It's the most elemental way you can think about reality. Think about it. When you were a baby, okay, if you smile a little bit, your mom gives you a small candy. If you smile a lot, you get bigger pieces of candy, right? And it's that sense of proportionality you learn when you were just this big, okay? That's what linear means. It means some kind of, roughly speaking, twice the input gives you twice the output. Okay, it's that proportionality, and this proportionality is constant. Okay, why is this important? Why is linear algebra important? Why isn't some other algebra part of what's, you know, I require? So I said the most basic thing you need to know is linear algebra. Not only is it the most basic, it's the most useful. Okay, it's the most basic, yes, but it's also the most useful because 90% of the problem can be solved with linear algebra. Okay, maybe 10% of the problem will require something else fancier, but let's say 90% of the problem you see in life can probably be solved with linear algebra. Okay, I'm exaggerating. It's probably more like 70. Right. So linear means it's simple. It corresponds to the sense of proportionality. What else does it correspond to? It corresponds to a sense of constant, right? Because that proportionality doesn't change. Okay, so it makes all the analysis immediately local, but immediately universal. What do I mean by that? If you're driving at 70 miles an hour, okay, presumably it's a straight road, right? Where would you go in half an hour? 35. Where would you go in 105? Does it matter if you start in Bangkok or in Cairo? Right? It's completely universal. It's that kind of thing. So you'll see that's why linear algebra is kind of like the easiest dynamics you work with. Okay, it's the simplest kind of information. All you need to do is some kind of rate of change. Okay, now that's the easy part, right? What the difficult part is This is like a bargain, right? I make your life easy by sticking to linear, but I make your life more difficult because this linearity, instead of applying to one number at the time, I'm going to apply to a whole bunch of numbers at a time. And that's why in linear algebra, you don't just study linear equation, you study things like vectors and matrix and so forth. Yes, individual operations are easy. There's kind of like, A multiplied by B, right? But you don't do it with just one X. You do X1, X2, X3, X4 up to 100. And that becomes powerful. Okay, so elementary operation, but complicated. Not complicated, but multi-dimensional. Okay, dimension of 1,000. By the way, any of you guys play games, like computer games? Okay, all the graphics you have is linear algebra. Okay, it's linear algebra. It's very elementary, multiplication and addition. That's it. All, because this is light coming in here, right? Reflect here, go to there. That's sort of like this sense of what from here to there is not going to change. It's sort of like a multiplication problem, okay? But you do it for every single point in the pixel, okay? So it's a simple, that's why things like this, it's called a game card. It's different from what's called a CPU. A CPU does complicated things. Okay, a GPU does multiplication and addition, but it does it in parallel for so many points on the screen. That's the power. It's a parallel. Now, why do I say that? I'll tell you why. Because this is the reason why the same mathematics that I studied when I was your age did not work. But work now as this AI, this visual recognition thing. You can say that the mathematics was around when I was about your age, but we didn't have the game card, so we couldn't make it real. Okay, it just didn't run. That's beside the point. Okay, so that's the linear algebra bit. So today, Monday or Tuesday, I don't know, our next 2 class would be basically linear algebra. Okay, now down here is calculus. So this is also a bargain. Okay, the bargain is the opposite. Instead of working of many things at once, when you study calculus, we are going to just study one variable. Okay, one variable, maybe 2 at most. Okay, we won't do many x1, x2, x3. Okay, so that's the bargain, right? But the difficult thing is now you don't have that kind of constant rate. Okay, it's not like traveling at 70 miles an hour. It's sort of like starting at 0, you accelerating up to 70 miles an hour, you go backward, you go forward, you stop, you slow down, and so forth. The dynamic itself is complicated. You don't have this sense of proportionality that stays with you. Okay, in turn, you're going to be studying univariate calculus. So basically just one x at a time. Okay. And with those 2, you will have the basic mathematics that would at least get you going. So if you go to applied digital intelligence, obviously you start to have to do something more, right? Multivariate calculus and whatnot. But that's it. So these are the 2 axes of foundation. Learn how to do simple things like multiplication, addition, but on a whole bunch of numbers at once. Or learn complicated dynamic, acceleration, deceleration, increase, adding cumulative value, but only with one variable. So those are the things that you will have to master by year 1, right? And this is something that is pretty much part of liberal arts education. Doesn't matter if you go to study philosophy or whatnot. This is something that's required to as a mental discipline. Okay. So having said that, okay, so algebra, okay, once I say this is where it comes in, okay, linear transformation, that's the sense that I was telling you about. Okay, linear transformation, it's simple as that, okay? You have something, AX, and okay, this is a sense of what happened when you multiplication, addition, and so forth. System of linear equations just means you have a lot of equations. The reason you have a lot of equations because you have a lot of variable, and that's the essence of many variable that I was telling you about. Okay, so this is it, just it. And all this is the topics that I make it as a scheme to cover. Now, this part I'm not going to teach you. Okay, this is called sequence and series. I'm using the textbook that I'm writing to teach you guys, but I'm not teaching the textbook, so I'll skip some and some section I haven't written and so forth. Okay, now let's start with linear algebra. And again, let's start with the object. What is an object? An object that we are going to deal with is just a number. So let's start with an. Okay. Now, last time I asked you to say the two definitions of number. What are numbers used for? Anybody? Come on. Exactly. Counting and measuring. Immediately, by the way, if you walk to your friends in the mathematics department, you will actually have two groups of mathematicians who don't really like each other. Okay? One group likes a discrete math, so they think of number as counting. The other group thinks of number as continuous, so they like continuous. And these people don't get along. Okay. So, by the way, counting and measuring. Okay. In a way, we can forget about, discrete and continuous and just think about counting. Okay, just think about counting. But if you count 1, 2, 3, but you don't count just 1, 2, 3, you count 1, 1.1, 1.2, 1.3, you're dealing with continuous mathematics. Well, not quite, but you're getting there. Okay. Conversely, you are from the continuous interpretation. You think math is a measurement, okay? But you measure against what? You measure against unit of centimeter and meters or whatever. So it becomes counting increment. So the point is, it's always on some kind of scale. And we talked about it last time, right? Nominal, okay? From now on, we are working with linear algebra. I am assuming we are working with full-fledged ratio scale. Okay, and this is important because it makes what we do very powerful. But when you use it in your real data, for example, we talked about last time the temperature, right? You cannot say just because it can be written as a number, you can always divide it. Okay, you cannot divide 70 degrees by 50 degrees. It doesn't make sense. It doesn't say it's 1.4 times hotter. Okay, so that's up to you. But the mathematics will be developed not at the nominal scale, not at the ordinal scale, not at the interval scale, but at full-fledged ratio scale. Okay, so it has all the information. It has 0, it has negative, it has big number, small number, goes all the way to plus infinity, minus infinity. Okay, and that's called a real number line. Okay, now from now on in linear algebra, they don't talk about number. They'll say if you have one number, it's a scalar because you measure it on a scale. It's the exact same word, by the way, scalar, scale. So a single number in linear algebra is not called a number. It's called a scalar. That's it. It has no meaning of its own. It only tells you how much of something. Okay? How much of something. Okay? Right? And it only has one direction, right? So it can go right or left. Or you can say up and down. So it only has one dimension. Okay? So you can do negative number. Okay, when it makes sense. Okay, so things like I'm starting here. Okay, 5 miles to the east, I can say east is plus, west is minus. I can do that, right? But I can't say you have a negative weight. Okay, just keep losing weight until you become negative. That doesn't make sense. So okay, that's a scalar. There is this thing called complex number. Just I write it here just to say it's here, okay? And some of you have studied in high school. Complex number, by the way, is the most useful invention for engineering. Okay, if you are an engineer, never mind. If you're a physicist, definitely. But at least, even if you're working with things like engineering, okay, setting up car suspension and whatnot, knowing how to play with I is very useful. Okay, we have to make some kind of budgeting thing. So I say, well, for bus size student, not knowing imaginary number wouldn't kill them. So that's my budgeting decision. Okay, so it's here. I'm not gonna work much with it, but it does happen in it's one of the most useful number creation. Now, okay, for those of you who took high school physics, right, you will have heard of the thing called vector. Okay, what's a vector from physics student? Anybody physics from took high school physics? Yeah, go ahead. Well, two things, right? Magnitude and direction. Okay, this is always a physics response. What's a vector? It's a direction associated with magnitude or magnitude associated with direction. Okay, that word, that magnitude, that is exactly what a scalar does. It says how much of something. But with a vector, how much of something means how much of travel in that direction. Okay, so you don't need, well, we can do a little bit of a, let's draw a picture, right? Okay, so you guys know you have this, right? This is very easy. I mean, nobody, this is not, oops. This is not a mystery to anybody. Let's pick a pen here and take this thick size, right? And oops, sorry. Okay, so you have this, right? So this is your X, this is your Y, okay? You've done this 1,000 times, okay? So maybe this is 1, this is 2, this is 1, this is 2, okay? And let's say I have something that start from here and go to here, okay? What is the magnitude? Magnitude is the length of this thing. Direction is where it's pointing. So I can have this thing sort of like make a round circle, okay? So keep constant magnitude, right? So that's the physics understanding. You have a direction and how far in that direction, including the other way, negative direction, that's your vector. Okay. With linear algebra, you try to decompose it because, you know, a direction, okay, I can do this, right? I can say that's the direction to the moon. Okay, you look at my hand, right? That's the direction. That's completely valid in physics, right? Well, in linear algebra, just as in computer graphic, you can only draw this picture if you give it a frame of reference. So even though the direction comes before frame of reference, right? I can point here and say, that's the moon, and you agree. In physics, it makes meaning. But in algebra, in computer graphics, I can't do this until I say, okay, well, this is an x-axis. This is a y-axis. And how much in the x-axis, how much in the y-axis. So right away, we are not going to think about arrow with direction. We are going to think about this number, x, and this number, y. In other words, the coordinate. Okay? So a vector, so first thing you think of, a vector is a coordinate. Okay, but if you draw a line from 0, 0 to that, yeah, you get an arrow, you get the direction, you get the length. Okay, but I want you to step back from that. Now, once you have 2 dimension, can you do 3 dimension? Yes, you can, right? And so when you locate somebody, okay, you are 3 steps away to the right, 4 steps to the front, and 5 steps up. Let's say you climb up ladder. Okay, so you need 3 numbers. Okay, well, that is what a dimension is. Okay, so this dimension, I'm going to have 3 numbers, right? Now, let's say we agree, okay? We are talking about meters. Do I have to say meters anymore? No, I don't. I just say go in X direction 3, Y direction 4, and the Z or Z direction 5. Okay, I don't have to say the unit. Okay, it's assumed it's a meter. Okay. Now, how about this? How about I change? I make it 4 number. 4 number. The first one is meter. The second one is meter. The third one is meter, but the fourth one is a temperature. Can I do that? That's what you're going to be doing. Okay. So you won't necessarily deal with direction on it's now completely general. You're not talking about location. You're not talking about arrow and mass and length and like in physics. Now this could be something else. Now temperature is still physics property, right? But I can say, you know, how happy is that person? Okay, so that's the fourth number. Now that number happens to be probably ordinal number, right? Because you can say somebody is more happy than the other person, but you can't say how much, right? So it's an ordinal number. This is where you start to mix in ratio, nominal scale, and so forth. But the essence is this. You have a whole bunch of numbers, and as many you have as many numbers as you have dimension. So now temperature is a 4-dimensional creature because it has 3 physical and 1 temperature axis, right? What else? It's a vector. You are a vector. Why are you a vector? Because, by the way, each dimension is a scalar, right? Okay. What if I say for you, for my student, the first dimension is age, right? So if you're 20 years old, that's your scalar number is 20. What's your second number? Maybe your height, your weight, okay? How far away is your house? So you can have as many dimensions as is interesting, okay? So physics, yeah, you're limited to 3 dimension, 1 time 4, right? If you work in superstring, you have maybe a few more, 6, 8, 10. But in physics, you have you know, that many dimensions. In life, in your data space, you can have as many dimensions as anybody. If you have a table of data, the first data point is the first line. The second data point is second line. How do you know the dimension? It's the number of columns. That's exactly it. As simple as that. Okay. So if you have data on something, I'm going to use M and N. Okay. There are M samples. Let's say there are M students. Each student is only interesting to me in 5 aspects: height, age, I don't know, eyesight, temperature, I don't know, something, okay, waistline, I don't care. Okay, so let's say I have 5. So if I am interested in those 5 attributes, okay, and I'm keeping the data set as a table for you guys, what does my table look like? It has many rows as there are students. It has many columns as the features or attributes I'm interested in, okay? In that case, what is the vector? The vector is a 5 number with fixed position. Okay, by the way, it has to be fixed, right? Because you can't switch X and Y. The first number is height, the second number is weight. If you switch them, you get something seriously silly. So it's not a set. Okay, it's not a set. So let's look at Mathematica. So with Mathematica, this is a set. Okay. Hello. blue. Okay, this is a set of three things. Okay, this is a set of three things. Now, I can say something like, is A in here member is blue in here? Okay, obviously it is. Member Q. Okay, true. Yeah. So it's just checking, right? Now, if I did this, oops. Okay, and I switch the order and I put blue over here instead, and then hello, does it matter? It doesn't matter, right? So the list is just a list. Okay, a vector is a list. Now, a vector is a list, but it's a list of number. So I can't have something like A and text. Okay, it has to be the same thing. So for example, it could be A, B, C. Okay, and A, B, C refer to some kind of numbers. Okay, so in linear algebra, okay, the element, the little guy, the A, B, C here, it's always scalar. Okay, and this is the dimension. Dimension is 3. Okay, now in programming, in Mathematica, as is, in Python, they use lists as the main data structure. So looking at alone, if I look at this alone, right, I can't tell if it's just a list. That doesn't matter which order comes in, or if it's a vector. Okay, that meaning has to be something that you maintain on your own. Okay, so while I'm talking about linear algebra, this will be a vector. This will be a vector. Okay, by the way, vector is not written like this. Okay, a mathematical vector is written like this. Okay, that's a vector. Okay, so let me say again, what is this? Okay, that's a data structure called a list. You can use it to store, 7 bananas, monkeys, elephant. You can store anything in here, color. Okay, but in linear algebra, it's only storing numbers. In other words, this is a scalar, this is a scalar, and this is a scalar. So you use that in Mathematica. But what you mean is this. Okay, this is called matrix form. Form, this is like form just means format. Okay, so in a textbook, I want my textbook to look nice, right? Even though the program I use this, I'm going to write it as that. Okay, so let's say this is the dimension, this is the location of something. Okay, ABC. Okay, ABC. Now, let's say this is a distance or location in 1 hour. What if I want to double the distance? Double A, double B, double C, right? So that's simple as that, right? Just 2 multiplied by ABC. Okay, right? You don't have to write multiplication. Just space would do. Okay, right. Now, this doesn't look nice, so I can do something like matrix form, right? Matrix. It's not my keyboard, so I don't have a good feeling for it. By the way, I just show you 2 shorthand. If I have a function, okay, I can put it in front. That's called the notation that you usually see in mathematical function, right? But you can also use in computing what's called piping. Piping is like, okay, mathematical function means you have a function, you have to supply me with an input, right? Supply me with something and I do something, that's called function. Piping would be something like if you're working in a factory, you're standing there, somebody does something upstream from you and then send it to you, and you do something, you send it down. That's called pipeline working. It's like an assembly. So this is kind of like the same thing as, say, you take this. So this is a function Okay, function does what? It does formatting. It does formatting. Formats what? Format this guy. So you get this. On the other hand, you can say, give me this, pipe it. This is called piping, okay? Matrix form. And it's the same thing. Okay, it's the same thing. This is just shorthand. I give you this because sometimes I myself get in the habit of writing in shorthand. So if you see this, you say, oh, what is that going? That, yeah, it means the same thing. Okay. So this is a function of something. This is something. Send it to me. I'll do something else. Okay. And I can certainly do something, and I can keep going. I can do this, and I can do something else down the line. Okay. So that it looks more like a production line, by the way. This is called a piping notation. Piping means like a pipe. You send it down the pipe, right? Pipe notation. You have that, I think, in most programming language. Okay. Another thing I haven't shown you is another shorthand. Sometimes I do so many things in front. I do this, and then I do something like okay, this, something like that. Okay. Okay, I can do this, right? Now it looks a little bit handful because you have so many brackets. So sometimes I'm so lazy. I don't want to do that. There's a shorthand for it. And this is just a shorthand, by the way. If you don't memorize it, that's okay. Instead of using bracket, you use app. This is like apply. Okay, this is like apply. So this is this thing, and this thing mean the same thing. Okay. Okay. Take three things. I interpret it as a number. I take exponent of each one of them. Then I show it in this in matrix form. Yeah. This one is a function notation. And this one is a post. It's the same thing. It's exactly the same thing. Okay. So I don't want you to be startled if you see sometime I quickly write something. Okay. I'm not going to save this, so it's no worry. Right. So scalar is a single number. A vector is a list of numbers like this. Okay. Now, one of the easiest way to create a list of number is a table. Okay. The other way is called array. You know, it's just two different construction. Okay. You saw table already, right? Let's say table. Now, here's where it gets a little bit more useful. If you have A, B, C, D, E, F, G, you can only go up to 26, right? So most of the time, mathematician or you would just say data point, and it would be x1, x2, x3. So let's say x control underscore I, right? Comma I, oops. I should bring my own keyboard. Comma. Okay. By the way, I want you to start. Yeah, you guys are doing it right. Just keying it along as you see. So I go to 10. Okay. So that's that, right? Okay. Oh, now bear in mind, every time you see this in a program, you know that a program uses this to store it. It's called a list. But if you are in the linear algebra class, you should not think of it this way. You should see this, and what should you see in your head? Okay. Oops. I don't like this keyboard at all. It keeps. Okay. This is what you should see. Sorry? Yeah, you can put it in front if you like. Yeah. So you can do this. The matrix form. Okay. Control minus. And you use the control hat for control. You have control here, right? X control minus, and it gives you a little box. You see that? You see a little box here? Okay. By the way, if you're new, right? If you're writing some kind of mathematical equation in Word, you have to use window, right? You have to go to like a palette, right? Have you done that? No? Well, you have palette as well. So if you're used to writing Word, this is a palette. So basic math assistant. And you can say, okay, so this is raised to the power, this is subscript, superscript, subscript, all kind of stuff. So if you don't remember, you say, I want X and I want something below it, right? So the important part to learn, it's sort of like just how fast you do things. But okay, now, okay. Now, obviously, we can do let's do a little bit of a callback. Remember manipulate, right? What if I want to produce many different lengths? So I can manipulate, okay? And instead of making it 4, I make it some kind of dimension D. Oops. D, right? And let's have a D going from, say, 3 to 11 in step of 2. Okay? Right? So, see? Ding. Oh, I forgot to tell you. Instead of changing manually, sometimes if you want to prototype or pitch your idea, and this is, let's say this is your app, right? You want to sell this app. Instead of using your hand, you can press the play button and it would just keep running like a movie. Okay? But obviously this is not an interesting movie. Right? So you have manipulate, you have 2 things. By the way, Mathematica doesn't care if you press and enter. So sometimes I do that to make things cleaner. Manipulate what? Manipulate what? Manipulate this function. This function does what? This function creates a table of xi, I going from 1 to d, and show it in matrix form. But this d here is up to manipulation. So this is manipulator right here. Okay. So manipulate always has 2 parts. Things you want to show and things you want to fiddle with. Okay. Right. What else? Well, what if I don't want X? This is just for fun, by the way. This is, I'm playing around. I don't want to play with X. I want to play with banana and apple. Okay. I want to play. So now it's not a number. So I have to keep it in the list. So now it becomes banana or an apple. See, banana or apple. Okay. So I'm just being silly here. Okay. Right. So this is how you can, play around with your whatever concept demonstration. So I'm going to do banana. I'm going to do apple. It doesn't matter. Okay. So notice now we have 2 things to manipulate. One is what exactly do I put here? And the other one is how long? How long? 3 to 11 in step of 2. So 3, 5, 7, 9, 11. This now X here. If I do the same thing, it's going to be number. Yeah, the enter just go to the next it's cleaner. It's cleaner. Yeah, you can do this in one line. It's not going to mess with. You don't have this thing in Python where a space of 2 means something and no space means something else or something. It doesn't matter. Okay. You can do this. Okay? But it's not very pretty. Okay. So let's say I do this. then it's going to be the same thing, right? Now, X is going to be 3, 5, 7, 9, 11. Okay, and the length is also going to be 3, 5, 7, 9, 11. So it's just kind of playing it. It's nonsense. It's not doing anything meaningful. Okay. Okay. The point is, this is what you want to show. Okay. And this is manipulate. But anyway, manipulate is a callback to what I was telling you last class. So it's don't need that. Okay. Now let's get serious. Okay. Let's get serious. I'm going to make array is another way of making a table, except it is in this case. Okay, I make an assignment. Okay, just type exactly like I do. Okay, that's a purpose. Okay. So you got here so far just now. It's okay. Yeah. Okay. So type in something. You can use your own name. I don't care. Okay. I just say X vector of dimension 3. This is my name. Name this thing. It's an array of X3. Now, when I use array X3, what it does, it gives you this kind of thing, an element. Okay, let me show you what it means. Okay. See? Now, why is this important? Because the vector, let's go back to the vector being the location. Okay. Now, again, vector can be any description of data, height, length, whatever. But let's go back to vector being the physical location, because it's very intuitive. So I'm going to have a vector of 3 numbers, right? The dimension is 3 because we live in a 3-dimensional world. Okay. Now I call this X vector 3, right? Oops. It's okay. Are you all right? You didn't break anything, did you? Okay. So that's this, right? Once again, this is how the data is kept, right? But in your mind, what are you thinking? What are you thinking? A vector is a stack, a vertical stack. Okay. So always think of a vertical stack. Now, I'll tell you what the horizontal stack is first, but right now I want to hard code this in your brain, just hardwire in your brain. A vector is a vertical stack of number. Okay. Vertical stack of number. Okay. So when you see this is a vector representation, but it should look like this in your head, right? Oh, good. I set my time. Okay. Half time. Anybody wants to go do your business? Okay. Let's take two minutes to do your 3 minutes or whatever. Okay. Up. But I'll keep talking because some of you want to see. So it's very easy. See, you can do this or. So array is the same thing as doing this, by the way. Okay. This is an array, right? So I can do the same thing. I can say it's a table. Come. Hold on. Okay, let me put my math. Some of you didn't realize this. I didn't realize, I haven't told you. When you shift enter, it's going to try to do the whole cell here. This is called kernel. Okay, this is called kernel. So if you write something that's an erroneous here, okay, so this is nonsense. This is nonsense, right? And this is sensible. When I shift enter, it's going to fail. Okay, it's not because this thing is wrong. This is correct. But you write something, erroneous. Okay. Now, what's important is this, okay? And I wish I have a blackboard. Okay. Okay, there is, okay, sit down, sit down, sit down. Okay, อย่าเพิ่งช่วยเพื่อนลูกเดี๋ยวค่อยนั่งกันเรียนกัน okay, my question is I have two things now. Okay, let's say I have this thing, I define this thing. Let's define this thing. Okay, I have this thing. Okay, I just go to an empty space. Okay, right? I also define this thing. Let's say do it together. Okay, fine. So now I have two objects. Okay, now I have to. Now remember, right now I'm going to restrict to the physical interpretation. A vector has 3 dimensions. Okay, let's say x is x here is the travel, the distance I travel first. Okay, so I go x1 this direction, I go x2 in that direction, then I go x3 up. Okay, so this is let's say east west, north south, east west, and up and down. Okay, let's do that. Okay, let's say it's a drone. Okay, I go x1 in the north south direction, I go x2 in the east west direction, then I go x3 in the up and down direction. Okay, so that's my x. Okay, that's my disposition. Now I have another instruction to the drone. That instruction say wherever you are, go y1 in the north south direction, y2 in the east west direction, and y3 in the up down direction. Okay, so the drone starts with x, and now I give it y. What's going to be the final position? Well, common sense, right? X plus y. So when I do this, notice, okay, this plus here, you used to add 2 things at the same time. Now each thing is itself a stack of 3 things. So this is called element-wise addition, right? Does that make sense? 3 plus 5 equal to 8. But instead of 3 plus 5, I have 3, 5, 7, and then 5, 8, 9. So when I add them, I just add them element by element. So this is element by element addition. Okay. Again, what does it look like? In your head, it should look like this. Okay. Now, by default, it's always going to give you in the horizontal because otherwise it wastes a lot of space. And this you know, you're working with x dimension 10. Every time you enter, it goes down this. So it doesn't make sense. So in your head, yeah, in your head, you should think of this. It's element by element addition, right? Simple as that, right? Okay. Now, what if I don't want to tell the drone to start from x direction and go to y direction? Yeah. แชร์ยังวะแชร์แล้วนะยังไม่ได้ stop share หรอก Okay. What if I don't want to start at x? I want it to start like in the same direction as x, but twice as far. So multiply 2 x vector (3). Okay, right? So it's 2 times x1 plus 2 times, and then 2 times x2, and then 2 times x3. So this is called scalar multiplication. So you have, again, the most important thing in linear algebra is to stop thinking of one number. That's not powerful enough. Okay, that's too easy. That's high school, that's grade school linear algebra. So in college linear algebra, you always work with a whole bunch of number at once. So you always work with vector. So a vector is a stack of number. It's so convenient because it stores all the interesting information. Now, if you happen to have interesting 11 attributes about you that are interesting, then that's dimension 11. Okay. For physical dimension is 3, right? For a map is 2. Okay. Now, so this here is whatever your object is. Okay. So let's say location, like I said. So what you can do with the location, you can double it. You can, by multiplying by 2, you can multiply by 3. You can tell it to go the other way, multiply it to -1. You can do that, right? Right. So what if I want to tell the drone to start at X and travel 7 times in the direction, in the distance of Y, but in the other direction? Well, that's easy, right? So I just do this minus, what is it, 7 times? Okay, and I don't have to put multiplication, just blank. Okay, just space. Y vector. Okay, right? V. So yes, it could. I just happened to because I use X and Vex, so no, it would not look nice. So I just naming convention for variable in Python, in Mathematica, you can use anything, okay, but no space, okay, no space, no dash, no space. Okay, usually I start with small case letter because the big case letter is usually the built-in function. Okay, so let's say this is my X, this is my Y. I start with X and I go 7 times the direction of Y, but in the other direction. So it's X1 minus 7Y1. That's in the north-south. X2 minus 7Y2 in the east-west, right? And then X3 minus 7Y3 in the up-down. Okay, simple as that, right? Okay, so what can you do now? You can think of a vector. You can store it in a program this way, but you can visualize it as standing up. Okay, it's always vertical. It's always standing. Can be anything. Yeah, can be anything. In this case, could be like kilometers or something. Yeah. So again, I'm not giving a real actual number. I'm just giving keeping it abstract. Now, so what can you do? You have a vector, right? Let me ask you this. A vector can have any dimension, right? And I just told you that you can add 2 vector element by element, right? What if they are of different dimension? Can you add them? No. That's what I mean by algebra, right? A human being can marry a human being and make a baby human being, right? But a human being and an elephant cannot get married. Same here. Each dimension is like a population. So if X has 3 dimensions, Y has 3 dimensions, you can do X plus Y. But if X has 3 dimensions, Y has 10 dimensions, you cannot add them together. It makes no sense. Okay, so let's say I have vector of 2 dimensions. Okay, oops, sorry. Okay, and let's see if this works. X3 plus Y vector 2. Yep, cannot combine. Yeah, see, human has 3 genes, elephant has 2 genes. You can add them. That's what it means by it's an algebra. Okay, so the dimension matters. Dimension matters, right? So now you can add. You can multiply a vector by a scalar. You can add or subtract element-wise vector of the same dimension. Okay, and here's something else which is really nice. Okay, what if you do this? By the way, have you used Excel? Any of you? Do you know what a sum product is? Okay. I'm trying to do a sum product. Sum product, okay? A sum product is not it's element by element, but instead of element by element, element by element, element by element, and produce the same thing, I want to actually produce something that is the sum, right? So what I want to do is this. I want to do x1, y1 plus x2, y2, that sum product, okay? Mathematically, it's called dot product. Why is it called dot product? Because in the early days, they use shorthand, they use dot. Let's see if we can do that. X three dot x y vector 3. See? Now, my question to you is this. What is the result? The result is not a vector. The result is a single number. So it's a scalar, okay? So in this population, you have vector and scalar. You can't mix and match vector of 3 dimension and 2 dimension together. Okay, that's no good. But you can mix 2 3-dimensional vectors and produce a scalar. That's okay because scalar is part of the system. Okay, so in linear algebra, dimension matters. Okay, the only time dimension doesn't matter is, well, it's a scalar. It's like no dimension. It's 1. Okay, so this is what you do. This is called x1 times y1 plus x2 times y2 plus x3 times y3. Okay. Now, mathematically, now this is in computing. This is in computing called sum product, right? Mathematically, by the way, you cannot take 2 vector that is standing and do element multiply, add, multiply, add. You have to make one of them lie down. Okay, so it's a little bit like yin and yang kind of thing, right? It's yin and yang kind of thing. So what it should look like is a little bit like this. Okay, so if you want to multiply x to y, in your head, it should look like this. In your head, it should look like this. Let me just write this first. Okay. Now, when I put transpose, okay. Oops. Okay. Let me show you this, and this is, by the way, this is the real way of doing mathematics. You separate. So row, I'm just going to define something else. Row, okay. Row is equal to, okay, just bear with me for a second, okay. X1 okay, 2. I just want to show you the result first. Okay. And then transpose. And then there. Okay. So I can only do this and To the right hand side is my y. But I don't transpose. Okay, so it's when I have this to the left and this to the right. I can't draw it nice. Yeah, that's what it's trying to look. Okay, it's easy with a blackboard, right? When you do some product in Excel, okay, you actually have 2 rows or 2 columns. You can do that, but mathematically you cannot. Mathematically, this dot product is not exactly the same as a sum product because it's an operation between a vector standing up and vector lying down. It's only when you do this that you can say x1 multiplied by y1 plus x2 multiplied by x2 plus x3 multiplied by y3. Now, here's a concept. Wait a minute. If they all have dimension 3, right? How do I separate? How do I distinguish between one standing up and one lying down? How do I make a note of it? How do I make a note of it? It's, it's 3, right? Well, you can visualize this as a table. Visualize this as a table. Instead of referring to this as dimension 3, and this is also dimension 3, right? 3 and 3, right? So how do you distinguish between one lying down, one standing up? Well, think of a table, okay? And this is where I introduce this thing called matrix. Matrix is like a table. A table doesn't have one number for dimension because it has number of row and number of column. So what is a vector that lies down? Anybody? It's a matrix of 1 row. What's a vector standing up? It's a matrix of 1 column, right? So in other words, this thing is dimension. Okay. So this thing here. Okay. Remember, this is the thing I'm talking about, right? This thing, when I show it, looks like this. What's the dimension? Okay. That's the function called dimension. Dimension 1 by 3. 1 by 3. And what's the dimensions of y? Three by 1. Oops. Sorry. 3 by 1. See that? Okay, come again. Sometimes I wish I can just use a blackboard, but we can't switch. Okay, let me see if I can do this. Okay, you have a scalar. You have a scalar. You have a vector. You have a vector. Okay, a vector has, say, this vector has 3 dimensions, 1, 2, 3. Okay. Instead of thinking it of a vector, I can think of it as a table or matrix. This matrix has how many rows? Same number of rows as the dimension of the vector. How many columns? 1. Okay. So if I say this is a vector, this is a scalar, this is a number, this here is a vector, say x1, x2, and x3. Okay. I can think of this as a vector of dimension 3. I can also think of it as a table, which I will now call matrix. What is the dimension of that? It's matrix of dimension 3 by 1. The word is by. So 3 rows, 1 column. Okay. In English, you just say 3 by 1. Okay. 3 rows, 1 column. So And I said, if I want to multiply this by another, do a sum product, I have to do it with another vector that lies down. Let's say Z1, 2, 3. This one, I can think of it as a row vector, or I can think of it as a matrix of dimension. Anybody? 1 by 3. Okay. And here's an interesting thing. If you put things that is 1 by 3 on the left, you multiply by 3 by 1 on the right. You write 1, 3, 3, 1. The 3 in the middle match up, and you get something that is dimension 1 by 1. Okay, let me say that again. Okay, so this is my, yeah, let's do this. Let's do this. Let's call this is my row vector. Okay, this is my row vector. Oops. This is my row vector. Okay, this is my row vector. And this is my column vector. Column vector. Okay, that's my definition. Okay, now what is the dimension of this guy? And what's dimension of column vector? See, 1 by 3 and 3 by 1. And what is the dimension of, and here's an interesting one. What's the dimension of product of row vector dot column vector? 1 by 1. See, this thing is 1 by 3 because it's lying down. This one is 3 by 1. So 1 by 3 multiplied by 3 by 1 is like some product, right? Okay. Now, you cannot do this between 1 by 4 and 3 by 1. Okay. The middle thing has to match. Okay. Right. So that's 3 operations. Okay. So now I'm going to introduce proper thing called matrix. Okay. Now this thing I'm making an assignment. Okay. When I do this, don't get confused. I'm creating a matrix. A matrix 4 by 5 is an array of A of 4 row, 5 column. Okay. Now, once I create it, I store it in the proper form, but I display it in matrix form. Okay. So, see that? Okay. See this 4? Okay. See this 4 is here. That's my decision. I make it 4 row, 5 columns. 1 row, 2, 3, 4. 1, 2, 3, 4, 5. And if you are familiar with matrix notation, you always put the row first. So what's this guy? A31. A31 means you go down 3 row, 1 column. Okay. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. But the second index going from left to right. 1, 2, 3, 4, 5. See that? Okay. I'll talk about that later. No, this one. Okay. By the way, I write 3 things down, so it's gonna give output here for this one, output here for this one, output here for this one. So it's in sequence, right? In the order. So first thing first, matrix form. So the inside thing, I'm creating an array of A, right? It has 4 row, 5 column. And so that's index 1, 2, 3, 4. 1, 2, 3, 4, 5, right? I display it as a table. Now, what's the dimension? Dimension is number of row 4 by 5. Okay. This little thing here is to get an element. This double bracket means to get an element. So if I have this thing, okay, it's going to give you, well, I'm not going to put in matrix form. So it's going to give you a whole bunch of numbers, right? So it doesn't look as nice because I haven't put in matrix form. Okay. But you can see that this is a row. This is a column, right? But it doesn't look as pretty, like I said. No, because in Mathematica, the way you handle vector is with a list. Yeah. So it is a list of lists, basically. Does that make sense? Okay, I want you to switch to notion. The mathematics notion is that it's an array. It has 4 rows, 5 columns. That's a mathematical notion, right? So in your head, when I tell you this thing, you should think it looks like a matrix. Okay, go down 4, go across 5. But in programming, Mathematica, Python, or whatever, it doesn't treat the matrix as an object. It treats it as a list of lists. It's a list of rows. That's what it means. See, this is the first row is a list. The second row is a list, but each list is separated by a comma and has a curly bracket. So it's a list of lists. That's the difference between programming and mathematics. Okay, mathematics is what you have in your head. Okay, this thing has dimension 4 by 5. So you say it's A11 all the way to A15, A21, A25, A31, A41, A42, 43, 44, 45. That's what you have in your head. But the computer doesn't take the whole shebang. You know, it doesn't say, oh, give me the whole lot. The computer only works with lists. So how do you represent that in a computer language? You say it's a list of lists. Okay, it's a list of rows. So that's what this means. Okay, but you know, if you're used to it, you don't have to keep typing matrix form. You can see this and you can see it's a matrix, right? But the reason I'm using this matrix form in this class a lot is because, again, I'm trying to teach you 2 things at the same time: mathematics and programming. Okay, so in your head, you should look at picture like that. But when you use it, when you manipulate in Mathematica, in programming, in Python, whatever, you work with list of lists. Now, here's the deal. Just as your dot product, right, is between a vector lying down and a vector standing up. A vector lying down is 1 by n, let's say 1 by m. Vector standing up is m by 1. You notice the middle dimension has to match, right? Right? Again, what if I do this? This is a production, right? This is a production. I have 2 parts, okay? 2 parts, right? Watch this. This thing, bam. And then add, okay? So this is row vector, column vector, multiply element by element, add them, and you get a product, okay? But I want to make an assembly line out of this. How do I do that? Well, what if I do this? Instead of having just 1 pair, I can have another guy wait in the bottom, right? Can I do that? Can I do that? So let's say each one is dimension 5. So it's 1 by 5, 5 by 1, 1 by 5, 5 by 1. But instead of having just 1 by 5, I have another guy in the bottom. So now what do I have? 2 by 5. 2 by 5 dot product or matrix multiply with 5 by 1. What do I get? The first one is 1 by 1. And the second one is also 1 by 1. And I put that in the bottom. So what do I get? I get 2 by 1. right? So instead of just doing this one at a time, I want to be efficient. Like, think of it this way. Remember, I told you that matrix algebra is so easy, but in return, you have to do with a bunch of things at once. So that be very efficient. This is industrial multiplication. Okay. So one multiplied by one, that's baby a multiplication. Some product, that's sort of like, you know, almost industrial multiplication, but that's not industry yet. Industry means you have a whole bunch of things you can do at once. So instead of this multiplied by this and you get a number, you have something at the bottom. So you have 2 now. Well, if I can put 2 on the bottom, I can put maybe 3 on the right, right? Can I do that? So now, I do this, right? Guess what's going to happen? I can do this for any depth. And I can stack this as long as I like. So at the end of the day, I'm going to get something that is M row. Okay, M. This is a text, plain text. Okay, so I can have A, which is an, let's call M by K matrix. Okay, so what is an M by K matrix? It has M row and K column, right? And then I have B, K by N matrix. Okay. In other words, that's okay. So what's A dot B? Anybody? A is M by K, right? M down K. And then you have B, which is K by N. So all the K match. Okay, keep matching. All I'm going to end up with is going to be M by K numbers, right? That's magic. So basically, this is industrial multiplication. Okay, matrix multiplication is industrial multiplication. Now let's see that in practice. Let's see that in practice. So let's start easy. Let's say A. Now we do this with mathematics now. Okay. A is equal to well, let's make this 2 by 3. Let's make it 2 by 3. Okay. So A11, A11, A12, A13, right? Comma. Sorry about that. It's not on my keyboard. A21, A22, and A23. Okay. So what's the dimension of this guy? Okay. What's the dimension of this guy? Check. Dimension A. 2 by 3. Okay. So let's do the same thing with B. So now I'm going to say B. Now B okay. I'm going to make B 3 by 4 by 5 by 4. Okay. There's a more efficient way of doing this, but let's do this. Okay. Now, if you use the array function, you don't have to type in, but okay, so that's that, right? So what's the dimension of B? 3 by 4. So what do you think is the dimension of A dot B? Remember, A is 2 by 3, 1, 2, 3, 2 of them. B, 1, 2, 3, 4 of them. So I multiply, match them by pair, and I get, oops. What it does is that you have to do this to make sure. Okay, it's 2 by 4. 2 by 4. Okay, so this is matrix multiplication. Now, okay, so what have we learned today? Let's make a little note. Let's make a little note. Okay, you can say that vector is vertical stack of n scalar. And then n is dimension of that vector. Okay, what can you do? What can you do? You can multiply vector by a scalar. You can add, subtract two vector of same dimension. Okay, you can do dot product between a row vector and a vector or a column vector. So by the way, sometimes I say column vector just to make sure that it's standing, but when I say vector by itself, without saying any word, it means standing. Okay, so you can, okay, now a row vector can be thought of as, what's a row vector? Of dimension 1 by n, and a column vector of dimension n by 1. Okay, you can do that, right? So that's a basic thing, and you get a scalar, not a scalar. Okay, now once you've done that, let's stack, okay, row vectors vertically and stack column vectors horizontally. Okay, it's the same thing as once you stack them, you becomes a matrix. Okay, then you can do matrix multiply. Okay, now this is basic, just the mechanic of doing things. Okay, I'm not giving you any meaning of why you're doing this. Okay, there's no meaning yet. Okay, so let's add some meaning. So when I multiply, this would be like, say, think something like double this distance. Okay, so that's the physical meaning. I'll give you a meaning. Okay, so let's think of that. And what did we do when we talk about adding two vector? So think of moving a drone from starting position. Okay, so that's, now what about this? You haven't given I haven't given you any intuition of the dot product. Anybody? Well, I can give you an example. Okay, I can give an example. What if the row product is equal to something like this? Okay, a row product is equal to 3%, 5%. Yeah, it's 3%, 5%. Okay, row vector, not row product. Okay, what is column vector is equal to, now this is your money. Okay, you're investing your money. Okay, let's say you have 100 baht and you have 300 baht. Okay, and then 200 baht, let's say. Okay, what do you think it's gonna be row vector? What do you think this represents? What do you think this represents? It's your interest earning. Because you have 200 baht invested at 3%, 6 baht. 200 times 3% is equal to 6 baht. You have 300 baht at 5%, another 15 baht. So what do you get? 200 times 3% plus 300 okay, times, what is it? 5% equal to 21 baht. Okay, this is like a weighted sum. Okay, you put your weight. So think of this as saving account, and think of this as investing in gold. Okay, so you invest 200 baht in this, you invest 300 baht in this, and increase the value by 5%. So that on average, okay, so this is kind of weighted average. The weight come from here. Now, if you actually invest equally in 3 and 5, say if this were 2, what would happen? You would get exactly 4%. It'll be the same thing. Okay, let's do that. Watch this. Okay. No, it's easy. It's your money. Okay, let's do this. How much do you get? 3%, 200 baht, 5%, 200 baht. So you get what? 16, right? You get 16 baht, right? What is 16 baht? Anybody? 16 baht is the same thing as 400 times 4%. Right? Right? What is 400? 400 is the sum of this. What is 4%? It's an average of this. Obvious, isn't it? If you invest half your money in 3% and the other half money makes 5%, altogether, what do you make? Half of it goes to make 3%, half of it goes to make 5%. So what do you make? It's like putting the whole thing in 4%. Right? So this kind of weighted average, you will see that happens all the time in life. Okay. In this case, it's not equal to that. It's not. Why? Because you invest more in higher percentage. So you're going to be something like 4, okay, 5.25% or something like that. I don't know. Okay. Right. Oops. Is it 5.25? Sorry, 4.25. Sorry, I don't have the same number here. Let me change a little bit so it's the same. Okay. Okay, so that's equal. Okay, now. Okay. Okay, now the math works. Sorry. Okay. See that? You have the opportunity to invest in 3% and 5%. If you put them in equal weight, it's the same thing as throwing the whole thing in at the average. But because you put a little bit more money in the 5% here in this case, it's like you're putting the whole thing in something that's higher than the average. Right? So let's do another case. Let's say I put 300 here and 200 here. This is not that interesting, by the way. So that's 9, so it's 19. Right? Am I doing the math right? I think so. Okay. So it's like I'm doing this at 3.8%. Okay. Right. Now, this is only a silly example, okay? Most people invest in hundreds of stocks. So it's not going to be 2 by 2. It's going to be 100 by 100 by 1 and 1 by 100, okay? In fact, anybody knows how many stock we have in Thailand? Listed stock, public company that you can trade it. 400, right? So obviously this example, this is why I want you to do it mathematically and programmatically, because in a program, you can read the 100 numbers. You don't have to multiply individually, right? So that's that. So this is going to be extremely useful. Okay. So you can multiply matrix. Now, okay, there is a special case, and this is very interesting. There's a special case. What if matrix, a square matrix, has same number of rows as number of column? Okay. Okay. What's so special about square matrix is that if you multiply n by n matrix with n dimensional vector, you get another n dimensional vector. This is also a form of algebra, right? Because you get something that's of the same dimension. Okay. And this, in fact, is what happened when you play video games. Okay. Video games is 3-dimensional. Okay. It's 3-dimensional. So a position in the game space. Okay. When you travel or when the light hits it, it doesn't matter. All the game programming is based on vector representation of a point in space. That point is 3-dimensional. Okay. You multiply that by a matrix 3 by 3, then you can move a point. Okay. So in your computer games, movement of anything and everything is done by multiplying by a 3 by 3 matrix. Okay. Now, because you are not putting the virtual reality glass, you're actually visualizing your 3D games in a 2D screen, right? There's actually another matrix that multiplies the three-dimensional object, 3-dimension, reduce it to 2-dimension. That matrix is 2 by 3, and that's a projection matrix that projects element in your game into a computer screen and you can look at it. Okay, so imagine you guys are in a game, right? You guys are in a game. Literally, you're my game object. Each one of you is a vector of 3 dimensions. Okay, if you're over here, let's say the 0 is over here, you over here, I say you move twice as far. That's multiplying by 2. You move in the same direction as this guy, so that's adding matrix. Adding vector in 3 dimensions. But the most general case is multiplying by a square matrix. So if you are a point in my 3D, you're in my game, you're a point in my game. I can move you anywhere by multiplying you with a 3 by 3 matrix. So all the game space, all the movement in playing games is multiplying by 3 by 3. Okay, but of course, eventually, this is in the game space. This is not a real space. You have to project it on the computer screen. Computer screen is only what? 2 dimensions. At some point, there's a 2 by 3 matrix that multiply your position and put it on the dot. Okay, that's what a matrix does. Now, I hate to complicate things a little bit. You know what a tensor is? Well, think of it as another dimension. Remember I told you that I can have 3 dimensions in position in space, and I add the 4th dimension as a temperature. Okay, what about this? What about in my game space? I have 3 dimensions, okay? But instead of 3 dimensions in space, I stack behind every single dot another element of color. Okay, and that color can be red, green, or blue. So it has 3 values. So it's actually a vector becomes, well, it's a tensor because every point has another 3 dimensions embedded in it. Okay, but that's a little bit. Well, I just want to throw that out because when you come to data science, a tensor will become something very normal. Okay, so what have you got so far now? You got something, okay? So a scalar is a number. Vector is a stack, vertical stack of numbers, okay, vector. And matrix is a table, rectangular array of numbers, okay? And later on in life, I just want to throw this out. Don't learn this. This is not important for you. Tensor is a rectangular cube of numbers. So so think of 3 dimensions that I told you earlier, but instead of hiding the other extra dimension as a temperature, this becomes something like color. Anyway, this is all you need to know. Okay. But tensor, by the way, is not from gaming. Gaming used tensor a lot, but it came from general relativity. It's more general than that, but okay. So I just want to give you the vocabulary. But all you need to do are 3 things now. Okay. So 2 days ago, when I asked you to add A and B, I want you to think of a function that does something requiring 2 ingredients, A and B. Adding is just a special form of that operation. Okay. Now, I want to think along that line, but I don't want you to think of a single thing like A and B being banana or being 6 and 7. I want you to think of a vector. Okay. So now you have a vertical stack of numbers. So it represents many things. And for the purpose of this class, just think of three: north, south, east, west, up and down. Think of a coordinate. It's the most intuitive. Okay. So I'm at the absolute center of the universe. You, relative to me, is 3 step north, 4 step east, and maybe 1 step down, okay, in 3-dimensional space, right? So every single point, every single thing, everything you're going to work with has dimension 3, okay? So you can add 3-dimensional vectors together, right? Because it's in the same world. That's what it means by the algebra. It's a closure. You're not adding 3-dimensional object to 2-dimensional object. You're not. You're not. In fact, remember I told you that in a game space, you are 3-dimensional object, but when I take you out there and project to the screen that's 2-dimension, that already breaks the thing. You're no longer working in 3 dimension. You see what I mean? So it's actually going to a different world now, from the virtual reality of 3 dimension to a physical reality of computer screen, 2 dimension. Okay. But within matrix algebra, you do this. You have to make sure that the vectors of the right dimension that they can multiply together. Okay. So think of it as the reason human being cannot reproduce with elephant is because we have different length genome. Okay. It's not just the length, obviously, but think of it that way. Okay. Human has this length genome. Elephant has that length genome. So you can never, mix and match to make baby human elephant. You can only make babies human and human because dimension match. Exact same thing with matrix algebra. The dimension has to match. And the dimension has to match in 2 cases. One, element by element addition. The other one is this kind of analogous to the sum product. Okay. So that's, so I'm going to tensor. I'm not going to teach you tensor. So let's wrap that. Okay. And now we're going to show, I'm going to show you, by the way. So this is a little, what I was doing before. Okay. If this is my A, notice what's A? What's the dimension of A? Anybody? 2 by 4, right? And what's X? X is 4 by 1. So when you multiply them together, you get, yeah, this multiplied by this, plus this multiplied by this, plus this multiplied by this, plus this multiplied by this, you get a single number right here on top. See, it adds some number. So it is 2 by 1, right? So 4 is 4 by 1. And well, we can try different dimension. Now, the way I wrote this little program demonstration, I make sure that the middle dimension always match. So that's okay. So I can do any kind of multiplication. Yeah. So the simplest case, well, let's make it 3 by 3. Okay. Yeah, that's 3 by 3. Okay. That's like you, north, south, east, west, up and down in my game space. I'm moving you by multiplying by this, and I get another one. So even though it looks, wide, it's actually just one number, right? So this is moving you in my game space. Now I want to project you onto the computer screen. I'm taking you out of that closure. So it's 2 by 3. Oops. There. Oops. Well, you get the point. Okay. I take something that's 3 dimension, multiply by 2 by 3 matrix. I get something that's down to 2 dimension, and I put it on a computer screen. Okay. So that's what the game card, this thing that people use to mine Bitcoin, that's very expensive. Okay. I'll show you more concrete example on Monday. Okay, so don't worry about it. This is a little bit, I just want to tell you that this is the head. We have 2 more, and that, you have plenty of time to practice. I just want you to know that this game card here, okay, does a lot of matrix multiplication. Again, because every time you're moving people in a game, in 3D games, you're just multiplying matrix, right? Well, in machine learning, what I do for a living, a neuron or artificial brain also has a lot of multiplication. And it has a lot of elementary simple calculation, but doing it in parallel, like a lot of them, a lot of multiplication on the side. So like industrial strength multiplication. So a lot of machine learning model, the one that I use, neural network, is based on a lot of matrix multiplication. And this is why, when I was your age, we had the mathematics of doing this AI, this facial recognition thing. The mathematics was there, but the computer only had the CPU. The GPU was not advanced. In other words, you don't have this thing that multiply things efficiently. Okay. Fast forward to around the turn of the century, NVIDIA started to make game card, doing very simple multiplication, but doing a whole bunch of them at once. So basically, a game card is a matrix multiplication machine. And it does it in such a massively efficient scale. You know, we're talking about 4x4, right? This thing is doing 1,000,000 by 1,000,000 or something like that. Okay, it's that kind of thing. So it's doing it so efficiently that you have 3D graphics. And then in the year 2008 or 2010, at that time, I was working with the bank, so not really working with AI anymore. Some AI researcher had the bright idea of saying, hey, wait a minute, we have game cards that does a lot of matrix multiplication. What AI was missing was matrix multiplication. So this guy very cleverly went to a game store, bought NVIDIA card, and used it to build AI machine. And that was the breakthrough in 2011. That was so clever. I mean, I thought it was so really clever. Think about transdisciplinary, right? You're talking about computer scientists who actually uses this technology built for gamers. Okay, very creative. I thought that was wonderful. I mean, that's a great moment, and it's been responsible for the breakthrough. And in fact, nowadays, my computer is a gamer's dream machine. I don't play games, but if anybody play games, would love my computer because it's got NVIDIA 3090 Ti or something, 3080. I think mine is 3080, but yeah, 30. Goเป็นแสนนะลูก but in my project machine, I have one that's 3090 and all that, but somebody else's favorite. Okay, yeah. So I have a perfect gaming machine in my office, but I don't play games. I use it to do machine learning, and it comes down ultimately to exactly this, except it's not 4x4, 5x5. It's gazillion by gazillion. Okay, so this is real. This is real. And from your point of view, those of you who are not going to machine learning or apply digital intelligence, you still need to know this, because when you handle your data is going to come in vector and matrix form. Okay. In fact, Excel is nothing more than a row of vectors. Okay. Good. That's it. Now we're going to do more. I'm going to give you more concrete example. It's still going to be 3-dimension, and down here I'll show you how when you multiply them, what happened when you find solution. Basically, this is it. Finding solution in 3-dimension and so forth. That's what matrix algebra does. Okay, and that's it.